In today's lesson we're going to talk about collision theory and the factors affecting rates. Now, collision theory is just a theory, and the theory is used to understand what affects the rate of a particular reaction. And if you could think of a jigsaw puzzle piece fitting into a puzzle just like on the right hand side here, the white jigsaw piece has to fit in with a certain orientation and a certain speed, otherwise that ain't going to happen. And collision theory seeks to understand why different reactions happen at different rates, so we're just going to explore that in a little bit more detail. So for successful reactions to occur, molecules must, according to collision theory, must collide with the proper orientation. If you look at the diagram on the right, only the top left will occur because that double bond is being attacked from below at the right orientation. The others are not at the right orientation. The second thing that's required is sufficient energy for the reaction to happen. So if you look at the GIF on the bottom left, the particles collide but with not enough energy in order for it to happen. And in the second instance, they're colliding with a little bit more speed and more kinetic energy and the right orientation, and therefore the reaction's going to happen. So to continue on talking about energy, there is this concept of activation energy. Now, activation energy is the minimum collision energy required for a successful reaction to occur. Think of it like a threshold. If the kinetic energy of the reacting particles is not above that threshold, then there's no reaction happening. A Maxwell-Boltzmann distribution curve is a visual way of showing the kinetic energy versus the number of particles, and it is a nice way to see how many particles have a high kinetic energy, how many have a low kinetic energy. And as temperature increases, usually kinetic energy increases also. And so if we look at what that might look like in a curve, if we look at the left side of the curve, there is a lot of particles, a high number of particles with a low energy. Now, the reaction will not happen until this green activation energy threshold is crossed. And so everything over on the right side has enough energy. Those small amount of particles have enough energy for the reaction to occur. So if we look at factors that affect the rate of reaction, the first one is temperature. By heating a mixture, you increase the kinetic energy and increase the chances of reactions. Well, hopefully that makes sense. Everything is sliding. The higher temperature slides across to the right, and kinetic energy is very heavily related to temperature, because temperature is a term used to describe the kinetic energy of particles. So as temperature goes up, kinetic energy goes up, and if kinetic energy is higher, there's more chance of better rate of reaction. So if we look at the simulator from PHET FET simulations, just going to use it to discuss this. I'm going to take pump some of these red molecules into this area. You'll notice the average speed on the top left here is 1,300 meters per second. And now I'm just going to start heating those molecules. And you'll notice that the temperature goes up, temperature in Kelvin. Also, you'll notice that the average speed is going up. And this increased average kinetic energy or increased temperature makes it more likely, if I were to introduce different molecules, that those molecules those reactant molecules would collide and smash together and form a product much quicker. So we've got a higher kinetic energy, because of the temperature, and if we increase those blue molecules in, there's a greater chance of reaction, and so that rate of reaction is increased. Second factor affecting rate of reaction is concentration of reactants. Increasing the concentration increases frequency of collisions. And if you can think back to those times when you were in bumper cars and you maybe smashed into somebody else in the bumper car, you know that there was a lot more collisions the more bumper cars there was more chance of having fun and bumping into somebody. And likewise with molecules, according to collision theory, the higher the concentration, the more chance there is of those collisions, the higher the rate of reaction. The third thing that is a factor when looking at rate of reactions is something called a catalyst. And these lower the activation energy, the minimum amount of energy required for a reaction to occur. A good example of a catalyst is sulfuric acid, and these catalysts, they work by lowering the activation energy. So this activation energy hill, they make it much lower, so the reaction is going to happen quicker, and they don't partake in the reaction, so the sulfuric acid is not actually part of the reaction, it just speeds it up. The fourth thing that is an important factor in terms of rate of reaction is surface area of solid reactant. An increased surface area increases the number of sites for a reaction to occur, and this is why we slice and dice our food. We chop up potatoes in order to get them to boil faster. And if you look as we move left to right here, these cubes, the smaller the cubes are, the more surface area they have, the more collisions can occur, the higher the rate of reaction. And the final thing that we're going to talk about is the pressure of gaseous reactants. So increasing the pressure forces molecules together, and that means there will be more collisions. So if this plunger is pushed down on the right, these molecules in there are going to collide much quicker, and they don't have as much room to float around. If you think back to the bumper scenario, our bumper cars would be in a much smaller area. There's going to be more collisions, and therefore there's going to be a higher rate of reaction. And finally, we're just going to recap on potential energy diagrams. We looked at the Maxwell-Boltzmann distribution curve, but PE diagrams are also another way to show reactions. There's exothermic reaction on the left, endo on the right. Exothermic reaction is where heat is given off to the environment, the surroundings, and that's why the delta H is less than of the products is less than the reactants, because some thermal energy was given off. And the opposite would be the case in endothermic reactions. But in both cases, you'll see this transition state, this activation energy hill had to be negotiated, and even greater in the endothermic reaction. And this is why exothermic reactions tend to happen more readily than endothermic reactions, which do require a catalyst to drop that activation energy. So that's the way very often that we show the reaction taking place. And just to show you again the catalyst, or the what happens to the activation energy, the impact of the catalyst, it's shown on screen. So hopefully you found that useful. You understand rate of reactions and the factors that affect it a little bit more than when you started the video. If you enjoyed the video, then just please remember to give us a wee thumbs up.